Welcome to the last lecture of the quarter for Cs231N. And it was great to see you guys at the beginning and now at the end. This lecture is a little bit of a departure. We're not going to teach any new materials in terms of algorithms. It's more a talk that I'd like to give to students to put a perspective both on a more longer term research evolution, but as well as another dimension that is important to today's AI, which we would call it the human perspective. So, for the completeness of the material, there's a little bit of an overlap, that you might see from other parts of this course, but, hopefully it makes sense in a fuller way. So the title of this slide or this lecture is What We See and What We Value, AI with a Human Perspective. And I know that some of you have already heard about this, is really the beginning, the origin of vision, both in terms of evolution as well as in terms of our technology. And we did talk about the first light that came to the animal world back 540 million years ago. And that was when animals, or trilobites to be specific, developed photosensitive cells to glean what the outer world is about. And according to zoologists like Andrew Parker, what happened is that because of this the onset of vision, it set off an evolutionary arms race where animals either evolved or died. And that arms race gave rise to the speciation or explosive speciation of animals, which now zoologists call the Cambrian explosion or the Big Bang of evolution. And of course, you wouldn't be surprised that vision is still to this day a primary sensory intelligent system in many, many animals. Not all animals use vision, admittedly, but many do. And that's also one of the primary sensory systems for humans. And we use vision to do everything from survival to work to entertainment to socialization to learning, development, and many other things. So that's the recapture or summary of evolution. And we also briefly talked about computer vision being a summer vision project back in the 1960s as an attempt to use a couple of undergrads to construct the significant portion of the visual system. And that was very in line with the history of AI, where we tend to have clarity of the North Star, but underestimate how long it would take. We are still probably experiencing that today, but a lot has happened, right? Like, you don't need me to tell you that from empowering self-driving car to understanding images to the generative AI revolution we're seeing, vision is playing a huge role and also in many parts leading the wave. So maybe it's time to just take a different look at this, both historically and going towards the future. Is where have we come from and where are we going? And this is an important topic to discuss, because a lot of what has happened will inform what will happen. So I'm organizing this talk in 3 chunks. First of all, building AI to see what humans see. And that's where we came from. That we were so inspired by human capability that we want to make machines that do the same. And then we'll talk about building AI to see what humans don't see. And then we'll finish with building AI to see what humans would like to see. Let's just start with the first one, building AI to see what humans see. Again, just a little bit of a review. Humans are so good at seeing. We know this. This is a very half a century old experiment showing us that even watching a video you've never watched, played at 10 hertz, which means every frame is only about on the screen for 100 milliseconds. You've never seen that. It's still no problem for human eyes to detect a target, in this case, a person, in this complex scene where you have no idea, a prior knowledge about what this person is. It really underscores the superb ability of human visual understanding, especially object-focused understanding. We also have briefly mentioned that around the turn of the century, neurophysiologists are measuring the speed of vision in terms of humans seeing complex objects in the form of brain signals, brain electrical signals, measured from EEG caps. And we see that differentiating or categorizing animals versus animals is a very complex task. Yet humans are capable of doing that at 150 millisecond after the onset of the stimuli. And this is remarkable speed given the wetware we have between under our skulls. Also, neurophysiologists have taught us that objects is a very important functionality in our visual intelligence in humans. So important that there are neural correlates in our brain, areas that are dedicated to object understanding, such as face areas, or place areas, or body parts areas. This shows that evolution has really spent time to hone in our visual intelligence skills when it comes to object recognition. So all this built up the history for the field of computer vision that a few decades ago, object recognition became a fundamental building block for visual intelligence, and we want to empower machines with that. And in order to do that, we define the problem, or at least the original problem, as given an image, how do we enable a computer to call out the objects, or what the object is in the image? That's such an effortless task for humans. But if you think about it, now that you've learned enough computer vision to know that mathematically there's infinite possibilities to actually recognize any object because of different lighting, texture, background, occlusion, viewing angle, scaling, and whatever, you name it. So this is actually fundamentally a difficult task. The history pre-deep learning is also very interesting. There were some pretty heroic attempts at solving the problem of generic, generalizable object recognition. And the first wave of attempt was actually very inspired by psychology itself. We self-introspect sometimes even to the detriment of over self-introspection. We think that humans compose parts, right? Like we look at objects, we can see geometric parts, and then we can compose them into different objects. And that idea of using pre-designated parts or shapes and to, compose them in specific ways was the first wave of object recognition. So these are different work or models coming from the 70s, 80s, or even going all the way to 90s of using different parts and configurations to recognize objects. Of course, it didn't really work. It's mathematically beautiful and simple, but it didn't work. So a second wave of object recognition pre-deep learning was actually a really important era in the field of AI. Is really the beginning of machine learning, statistical machine learning. It was the marriage between computer programming and statistical modeling. And with that marriage, we start to realize the world is so complex. These problems, these intelligence problems, whether it's visual intelligence or language intelligence or other kind of intelligence, in order to generalize, we need to learn learn the parameters. It's very hard to use hand-tuned models to get good learning. We now know we need data, even though we didn't at that time know how much data, but we also know that we need to design or architect statistical models so that they have the capability of learning through different learning rules. And because of that, we saw a blossoming of models in that era where we're learning, random fields or Bayes nets or support vector machines and all that. And in fact, a lot of progress was made by the time we are in the first decade of 21st century in object recognition, that we even have international benchmarks of a small number of object classes to encourage everybody to compare their algorithms. So we're inching together. The last unlock for object recognition, as we have learned, again goes back to cognitive science. So this particular psychologist, Irv Biederman, had long conjectured that humans can recognize a huge number of objects. And this is intuitive for our common knowledge, but he actually put a number on it. Well, I personally call it the Biederman number, which is that by, age 6 or 7, children, he conjectured, were able to recognize about 30,000 to 100,000 different visual categories. And he used this, where did he come up with this number? It's a combination of looking at dictionary, the number of nouns, as well as visual studies of how kids recognize different objects. But it's a number that's pretty daunting and pretty sobering for the field of computer vision, because up till now, this is middle of the first decade of 21st century, we were working with tiny number of object categories and a tiny number of images to work with compared to what humans experience. And this was, as you know, the onset of the motivation for ImageNet project, which took this Biederman number really seriously and we constructed this data set that is on par with what the psychologist Irv Biederman conjectured, which is around 22,000 object classes over 15 million images. And of course, that's the beginning that you start to come into this class, is that because of the large data provided by ImageNet, we start to see that powerful algorithms like neural network, at the beginning it was convolutional neural network, of course now we use transformers and all that, start to really show their power through big data. And this is a generic slide for those people who didn't learn about this. I'm going to skip this because you all know this. So the quick history is, as soon as we have ImageNet, as soon as we use convolutional neural network a few years after the beginning of ImageNet, we saw this door blasted open in terms of solving the problem of object recognition. Now we have algorithms that we can take to look at any picture in the world and be able to recognize objects in the big or small and in any kind of, orientation. It's not, is it 100% solved? No, there's always long tail problems we can solve. But as far as industrial application goes, this has come a long way and really has been a matured problem. And of course, all of you know, and all this came at the convergence point, which is the year 2012, where the ImageNet Challenge provided the data for the convolutional neural network, and they used 2 GPUs at that time, and the 3 ingredients come together and brought the moment of deep learning, the birth of deep learning. And in this class, we also talked a little bit about different various architectures that ImageNet Challenge engendered throughout the past decade or so, in terms of, convolutional neural network or ResNet and so on. So that's the beginning really about deep learning revolution. And of course, in terms of the quest for visual intelligence, we're not going to stop at just being able to label objects in a scene. For example, in these two scenes, right? If you just label objects, you'll think it's just a llama and a person. But if I show you the second scene with the llama and the person, the story is completely different. Even though you have the same object, you have very different relationship. So cognitive scientist, once again, was the head of computer scientists, and inspired us to think about visual intelligence beyond just naming objects or categorizing objects. In this particular paper, Jeremy Wolf, who is a pretty prominent psychologist, wrote this beautiful paper that called out that relationships between objects must be coded as part of our understanding of complex natural scenes. And inspired by that work, the field of computer vision started to look at how do we understand relationships. And this is early work. You guys got a lecture from Ranjay, and last week, last week, this was his PhD thesis, looking at learning object relationships using scene graph as a representation. In this case, scene graph is defined by these entity nodes that are objects, and their relationships are defined by the connectivity between the nodes, or sometimes they have attribute relationships that defines the particular objects. And even a scene as simple as this, with mostly just two people, one feeding a cake to the other, you can form a very dense scene graph because of the richness of the visual scene. And this was Ranjay's thesis after the image that object recognition era, where we build a data set called visual genome, where we try to put together object relationships, also story descriptions. And one of the work that Ranjay did, I thought that was really fun, was zero-shot learning of unusual object relationships. For example, it's not unusual to see person riding a horse. It's not unusual to see person wearing a hat. But it's unusual in general to see horse wearing hat. And in the era of big data training, it's hard to get this kind of data repeatedly because you just don't have too many of that. But using this compositional scene graph representation, we're able to learn the more common relationships and then derive uncommon relationships in that representation. And again, this is another example of zero-shot learning where, person sitting on chair and fire hydrant on the lawn or on the field are all common relationships, but person sitting on fire hydrant is the one that would not. It's hard to get data, and we're able to do that, to make that happen. And this is just a figure from the paper that shows that Ranjay's work at that time achieved state-of-the-art recognition rate compared to many other methods. But relationship is not enough, right? The ability to actually tell a story that is a lot more richer, or also using natural language, is actually the next big goal. So around the year 2014, we start working on that problem. And think about it, that's just 2 years after the image that Alex, that moment. But the field was starting to evolve so fast. We're so inspired by what we can do using a combination of convolutional neural network as well as a language model called LSTM. And this is the thesis by Andrej Karpathy, that we were one of the first teams that showed how to do image captioning or storytelling, as well as dense captioning which is also part of the work that Justin Johnson did. And I know he's one of the co-instructors of this course. And that was around the time between 2015 to 2018, a lot of work has happened to solve the problem. Of course, today, using multimodal LLMs, we have taken the solution of this problem even to another notch. But this is the beginning of that line of work. And frankly, I myself, as a computer vision scientist who entered the field at the beginning of the century, was very surprised by how fast our field was able to solve this problem as soon as we've got data as well as neural network algorithms. But a much harder problem is actually in dynamic scenes. In dynamic scenes, we tend to have much more complex relationships, much more complex movements, and the camera, also the camera movement or the entity, the actors within the scene can do a lot of different things. So in this work, that a collaboration with Yi-Sun and a bunch of students in our lab, we call it multi-object, multi-actor activity understanding. This is a much newer work. We only published this a couple of years ago, to capture the relationship between these actors and their activities in dynamic scene is still, I would say, an unsolved problem. And this will have profound implication. You know that you're in Silicon Valley, so you're hearing so much excitement of robots, for example. If we ever dream to have everyday robots that work amongst us, robots need to solve this problem, understand how complex the scene is, what people are doing, who is doing what is next, and this is an unsolved problem. Also, you know, in addition to what I have shown you, you have learned a little bit in this class and related computer vision problem, but we didn't have time to elaborate. For example, 3D computer vision or human pose understanding, and of course, generative AI and generative models. So this is just to show you that the field of computer vision since the rebirth of modern AI has been just moving extraordinarily fast. But the take-home message in this section for me is that two things. One is that data compute and neural network algorithm truly have converged about 10 years ago or 13 years ago. And that was the moment that modern AI or deep learning revolution has happened. But the history of that and so much of the problem that we have been working on is truly inspired by cognitive science and psychology and neuroscience. And that to me is is going to continue to happen, is that we will continue to be inspired by what the brain can do or how the brain does things. And also we'll continue to use AI to help our brain research. So there is a very intimate relationship between today's AI and cognitive science, neuroscience, brain science, and all that. So that's the first section. And of course, a lot of people, students and collaborators have contributed to what I have just presented. Now let's talk about going beyond just building AI to see what humans don't see. This is where pushing AI beyond the capability of humans, or you can call it superhumans. For example, most people don't recognize a ton of dinosaurs. You can probably name a few. Some kids really can name a lot. Well, let alone thousands and tens of thousands of bird species, or tens of thousands of car categories. So this is the line of work that I call fine-grained object categorization. Humans are just not that good at it. And this is still a problem that I don't think we're fully solved yet, to be honest. In this generative AI era, especially we're talking a lot about multimodal LLMs, this problem has somewhat been neglected, or it just is not a mainstream problem. But it really will, still will come and play an important role. So in this early work of fine-grained bird species recognition, we put together, a data set. Actually, we used a data set of 4,000 birds. And as you can see, as we go down the tree of the species, the eras, actually, as we go up the species, as we have generalizable, more general names, the error decreases, but which means it's a convoluted way of saying by the time you're in the fine-grained level, we still make a lot of errors. The algorithm are still not totally ready. Another work that I find fascinating is that a few years ago, a group of students and in my lab trained a fine-grained car classifier in terms of make, model, and year. It turns out after 1970s, there are thousands of car models that are defined by different make, model, and year. And then you can we took Google Street View images from 200 or 100, I think, major cities across the country. And then we use the fine-grained car detectors to detect what are the cars on the street of these cities. And we use it as a lens to study social patterns. For example, what is the pattern here I showed? Education patterns. Car models and education patterns are highly correlated. Or income patterns, highly correlated. In that paper, we show voting patterns, highly correlated. Or even environmental, patterns, highly correlated. So it's a really interesting way of using computer vision as a lens to study our society. And no individual human, not even a collection of humans can do this easily at all. So AI is really pushing the boundary of what humans can see.